So our mathematician spotlight today is this guy, Kwadwo Antwi-Fordjour. He's visiting us from Earlham College, and he's giving a colloquium today at 4:30 in Science Center 181. So he does differential equations, and he studies this animal called the hydra. Do you know it? It's like hard to see, right? It's sort of transparent. And it has this amazing quality that if you cut off its head, it grows it back. And so not only is that cool, but he models that with differential equations. So he's going to be talking at 4:30. He's also a job candidate. So he's interviewing for the same job that I have, 3-year visitor. So if you would like him to be here next year, you come to the talk, meet him, and then tell people that you want him to come. Take like control over your environment. So that's the idea. I'll be there, and I'll be talking to him from 2:30 to 3, and that's why I won't be in office hours. So that's good. Okay, good. So last time we talked about, let's see, optimizing on a constrained region. So like the state of Colorado, for example, we want to find the high point. And we talked about how you have to check the interior for like mountains. You have to check the edges, the boundaries, for like just places where things are high on the boundaries. And then you have to check the corners in case the corners are up higher than the other places. So today we'll do an example of that, and then we'll talk about this really cool idea, Lagrange multipliers. I think it's the coolest idea in this class. So that's pretty neat. We'll do it today, and then we'll do more applications of it on Monday. Yes, after our exam on Friday. So that's the plan. Yeah? Okay. So let's, just as a review from last time, let's do an example. Let's find the absolute extrema, or the maxes and mins, that's another way of saying the same thing, of the function f of xy equals x times y on the closed unit disk. So the closed unit disk is like the unit circle except filled in, and we have this function x times y. So x times y, let's see, in this quadrant x times y is positive. In this quadrant they're both negative, so x times y is also positive. And then here they have different signs, so x times y is negative, and here it's negative. So we might expect to get maxima here and minima here. Maybe that's what we expect. Okay, let's do it. So first we have to find critical points, places where the gradient of f is equal to 0. So this is on the interior. So let's do it. So the gradient of f, can you say what it is? Derivative with respect to x is y, yep, and derivative with respect to y is x, and we set that equal to the 0 vector. So we get from this y equals 0, and from this line x equals 0. So 0, 0 is the only critical point. So we could add this to our list. So candidates, 0, 0, and let's find f of 0, 0. When we plug in 0, 0 to this function, we get 0. Okay, so f of 0 is 0. Okay, so let's do the boundary. So find critical points of boundary function or functions. So we need to somehow parameterize the boundary of the closed unit disk with one variable. Can you do it? Yeah, this is something we've done before, maybe. So x is, if we use x equals cos theta and y equals sine theta, then the whole unit circle, which is the boundary of this disk, is parameterized by just the variable theta. So this should work. So then we have f of xy is x times y. So f as just a single variable function of theta is x, which is cos theta, times y, which is sine theta. So this function tells you, for any theta, what the value of your function is. So as we go around, it tells us how high it is. Sometimes it's going to be positive, sometimes it's going to be negative as we go around. This function on the unit disk basically does look like a Pringle. It's sort of, or a saddle cut into a circle. It does go around like this. So now we want to take the derivative and set it equal to 0 and solve for theta. So f prime of theta, okay, we have to do the product rule. So the derivative of the first times the second. So the derivative of cosine theta is negative sine theta, and then we multiply by sine theta, so sine squared theta, negative sine squared theta, plus the first times the derivative of the second. So cosine theta times cosine theta. So plus cosine squared theta. There's the derivative, and we want to set that equal to 0 and solve for theta. So let's see, we would get here cos squared theta, let's move this over to the other side, equals sine squared theta. But then cos theta is just x. So this is x left is x squared. And sine theta is just y. So the right is just y squared. So this tells you that x is plus or minus y. So it tells you that where critical points are, well, they are either along x equals y or along x equals negative y. Okay, and so what we want to find is these 4 points on our constraint curve where x equals y and you're on the unit circle. So if you do this, you will find they are, what, like root 2 over 2 comma root 2 over 2. That's this first one. Negative of both, so negative root 2 over 2, negative root 2 over 2, and then the opposites. So root 2 over 2, negative root 2 over 2, that's this one, and negative root 2 over 2, root 2 over 2. That's this one. And then now if we compute f at each of these points, so f is just x times y. So if you multiply these two guys together, you get 1/2. So this gives you 1/2. This one also gives you 1/2. This is negative 1/2. And the last one is negative 1/2. So these are we had a candidate critical point in the middle, and these 4 along the boundary. And these 2 are the maxes. So these 2 are the maxes. And these 2 are the mins. Yeah, or the absolute max and the absolute min on the closed bounded region. Yeah. Yeah, questions or ideas? Okay, so there's that way that we've done. And now we will see a new way of doing just the boundary curve part. So if you would, on your sheet, you have like some topo lines for a mountainous region, and you are a shepherd. And so can you please make a blob, any sort of a blob, maybe an interesting blob with no corners, just nice smooth. And that is your sheep grazing land. And then you're going to walk around the boundary and find the highest point of the fence of your land and the lowest point of the fence of your land. Okay, do it.
So this is the point of elevation because this is where the topographic lines are at their maximum. And then here, this is your lowest point of elevation. This is your min, because your topographic lines are at the lowest point. That's so cool.
Yeah. Okay. Questions, ideas? Yeah?
What did you say was the lowest point? How come it's not that?
Wait, come here. Have some chalk?
Oh, nice.
Say what you mean. Good?
How come it's not this point? Wasn't that?
Yeah, I didn't realize that. Because technically this is the min.
So can you say what you realized? And
I think this is the lowest point, and yeah.
because why?
Because it's marked to a low elevation, and that's at the higher elevation.
Nice, great. Thank you. Okay, great. So, okay, here's one more question. Just one more question. You found that this was the highest point, and now we decided this is the lowest point, but you also had to check this point. Can you circle? You still have a chalk, yeah. Can you circle all the points whose elevation you had to check to find your max that you checked, just to see which is max and mins? Yeah, all the points you checked. Or just some others that you checked. Yeah, nice. Put a big circle around it so we can see it. Okay. Yeah, nice. Yeah, why? So can you say, like, why? Why did you check, say, this point here?
These are like the most outward points of the circle.
Yeah, the most outward points of the blob, yeah. Yeah, nice. Okay, I don't think you checked this one, maybe. Because maybe you did. But, so here's one thing. So the points to check are maybe the points that are, like, furthest out in the level curves. So it went out, and then this one went out. But the points you want to check are places where your constraint is tangent to the level curves. Yeah, I saw this on a lot of people's paper that you had the furthest out points. So you might want to check, like, well, maybe you can see that that's not going to be one of the points, but this is a point where they're tangent. Here's a point where they're tangent. Maybe here's a point where this is tangent with some level curve that we didn't quite draw. This one maybe. This one maybe. This one. There are many, many, many of them in this picture, which is why it's so nice. Yeah, so you'd have to maybe check all of these. Here, what? Here you are climbing, and then you get to a high point of your fence, and then when you're continuing to walk along the fence, now you're walking downhill. You're walking downhill until here. Now you've stopped walking downhill, and now walking along your fence, you're going to walk uphill, 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 till we get to here. And then we're going to start walking downhill, and then uphill again. So sort of like on your fence journey, walking along the fence, there are like local maxima and local minima. And so we'd want to check all of those. This one, I'm so glad that you picked out this one, because it's far out in the fence, like it's near the end of the map, but we're just walking downhill here. So we maybe don't have to check it, because we know that if we keep going downhill, we'll get a place with lower elevation. Or if we keep walking uphill, we'll get a place with higher elevation. Yeah. Yeah, nice. Thank you. What a lovely blob. Very nice. So the insight here, Lagrange's big idea, is that maxes and mins of the function on a constraint curve happen when the constraint curve is tangent to a level curve of the function. So occur where the constraint curve, so the fence in this case, is tangent to a level curve of the function. Because let's think about it. So suppose I said, I think this point is a local max of the function on my constraint curve. Well, it's not, because we're crossing a level curve here. So there's some direction that you can go and increase the function. So it couldn't possibly be a maximum. I can go along the constraint and increase my function. And that's true all the way along until I get to a place where my constraint curve is tangent to my level curve. Then I can't increase anymore. So I'd have to check this point. It might be a local max. That's the idea. Anytime they cross, there's some way you can go to increase or decrease your function. By the way, it might not be a level curve that we've drawn. So it might, like, right, this one or this one is sort of between two level curves. But you can draw in level curves at any level, even like half levels or pi levels or something like that, any level. So that's the big idea. And the way that we can do this, so that's the geometric thing that's going on. And then algebraically, notice that at this point, let's see, here the gradient vector of f, those are the white curves, white curves are level curves of f. The gradient vector is perpendicular to the level curve and points in the direction of increase. So the gradient of f points in some direction like that. And then if I had an equation for this beautiful orange constraint curve, then it would be g of xy equals something, and it would have a gradient vector. And it would point, well, either, it would also be perpendicular to the curve. So it would either point here to the right or this way to the left. So maybe it points to the right like that. So this is the gradient of g. So the Lagrange multipliers equation says that the gradient of f and the gradient of g point in the same direction because their level curves are tangent at that point. But they might be, yeah?
I was just wondering what the gradient for the constraint curve means exactly.
Yeah, what the gradient for the constraint curve means. Well, you would have, like, here it's not clear what our function is for our constraint curve, but if it was something like x squared plus y squared equals 1, our unit circle example, then the gradient would be like, well, what if you had x squared plus y squared equals 2? Then you'd have a level curve of that same kind of constraint further out. And so the gradient would point out of the circle and perpendicular. Yeah. So this Lagrange multipliers equation says they point in the same direction, but they don't have to be exactly the same. Like here, g is half of f. Gradient of g is half of gradient of f, so it has to be some multiple, and so we call that Greek letter lambda for Lagrange. So this is just some constant. Yeah. So this is the Lagrange multipliers equation. Other questions or ideas? Good. Okay. Well, let's try it out. So let's try it out on our same example from the beginning. So our example was to find absolute extrema of f of x, y equals x times y. In that case, it was the closed unit disk, but Lagrange multipliers only works for a constraint curve. So let's find it on the unit circle. So in this case, we wish to maximize and minimize some function subject to the constraint that some g of xy, which is some function, is equal to some constant. Okay, we'll have to fill that in. Okay, can you say what it is? We want to maximize what function? Xy, yep. Subject to the constraint? Yeah, x squared plus y squared equals 1. Yeah, that's our constraint curve. Cool. Okay, so geometrically what's going on is that our function, x times y, let's draw level curves for it. So if x times y equals 1, for instance, we get a hyperbola here and here. So the two branches of x plus y equals 1. And if x times y equals 2, we get these two branches. X times y equals 3, we get these two branches, and so on. So these are level curves for f of xy equals x times y. And then our circle, and then we also want the negatives. So if x times y equals -1, we get these two branches, and equals -2, we get these two branches, and so on. Okay, so those are the level curves for the function. And then we have our constraint curve, which is a unit circle. So something like this. Okay, so there's our unit circle. And so Lagrange multipliers is going to pick out points where the level curves are tangent to the function. That's the dream. That's what it's supposed to do. So let's do it. So a Lagrange multipliers equation says the gradient of f is some multiple of the gradient of g. So let's do it. Gradient of f We've done that before. Derivative with respect to x is y. Derivative with respect to y is x. And that's equal to lambda times the gradient of this function. So 2x, 2y. So 2x, 2y. So this tells us, for looking at each line, here y equals lambda times 2x, and x equals lambda times 2y. So that's two equations in three variables, because we have x, y, and lambda as our variables. But we also have our constraint equation, x squared plus y squared equals 1. So this is three equations and three variables. So you can solve it however you want. But I'm going to suggest that you use the lambda parts to eliminate lambda and find a relationship between x and y, because it has some sort of geometric meaning. So let's try that. So one strategy is to eliminate lambda and find a relationship between x and y, and then plug that into the constraint. Okay, so let's do that. So we have these two equations with the lambdas. So we had y equals lambda times 2x, and x equals lambda times 2y. One thing you can do is solve for lambda, and then set the two things that are equal to lambda equal to each other. The thing you need to be careful about is that you have to be dividing by x. So you have to carefully justify why x is not 0 at a max or a min. For this function, it's pretty clear that x is not 0 at a max or a min, because this function takes on positive values, so 0 isn't a max, and it takes on negative values, so 0 isn't a min. So you could say x isn't 0 at a max or a min, so I can divide by it. But it's a little bit more elegant if you can just multiply by something. So I notice that if I multiply the top equation by y and the bottom equation by x, the right-hand sides are equal. So I can multiply this equation by y and this equation by x, and then the two right-hand sides are equal. So I have lambda times 2xy equals lambda times 2yx. So I have y squared equals x squared. And so this means y equals plus or minus x. Okay, so geometrically what's going on is that in using these two equations, I've only used sort of the form of the constraint. So the constraint is of the form like x squared plus y squared equals something. So things that are of the form x squared plus y squared equals something, those are circles centered at the origin. So it's this whole family of circles here. So the Lagrange multipliers equation is looking, if you will, at all these circles and looking at where the family of red circles, so this is the family of curves of the form x squared plus y squared equals something, and saying, you know, where these things are tangent, the reds are tangent to the blues. Well, along here, that's where the reds are tangent to the blues. And also, along here, that's where the reds are tangent to the blues. And along here, and along here. So it's picking out that these tangencies occur between these families along the lines y equals plus or minus x. So that's what using the Lagrange multipliers equations pull out where these lines of tangency are, or curves of tangency in general. And then you say, okay, that's cool. I'm so glad that I know where these families are tangent, but I'm only interested in one particular constraint curve. I care about this one. X squared plus y squared equals 1 exactly. Just 1, not any other number. So now we plug this into our constraint. So our constraint in this case is x squared plus y squared equals 1. So we have done this before. We did it at the beginning. If x squared plus y squared equals 1 and y equals plus or minus x, then we get our 4 points. So we get root 2 over 2, root 2 over 2, and negative root 2 over 2, negative root 2 over 2, and negative root 2 over 2, root 2 over 2, and root 2 over 2, negative root 2 over 2. So if you plug this into this constraint, you get these points. And we already plugged in the function value. We found that these were maxes and these were mins. Yeah, so that's the idea. Yeah. Yeah, questions or ideas? Yeah. Yep. So when I had this line, lambda equals 2xy equals lambda 2yx, so I was setting the right-hand sides of this equation equal to each other, and therefore the left-hand sides have to be equal to each other. So something like y squared equals lambda times 2xy from the first line. Oh wait, and 2xy is also equal to x squared from the second line. So this is from the first line, and this is from the second line. Therefore, y squared equals x squared. Yeah, other questions? Okay, if you're willing, I think now is a good time for a class photo. So let's do another one. Okay, here's our next quest. We want to find 3 numbers whose product is as big as possible, whose sum is 100. 3 numbers that add up to 100 whose sum is as big as whose product is as big as possible. Okay, so I have an idea. You could use 10 and 10 and 80. 10 times 10 times 80 is 8,000. It's pretty big. Can you come up with a bigger one? Make them all equal. That would be bigger. Can you come up with another one that's bigger? Yeah, negative a million. Negative a million. Negative a million. Negative a million plus 1. And?
Negative a million, then positive million plus 100.
Yeah, I think that's how you, okay, negative a million, and 2 million plus 100. Yeah? Because I think that those add up to 100. And their product is pretty big, yeah? Okay, can you come up with a bigger one? Bigger product? Yeah, okay, infinite, we're not allowed to use infinity, but you could use a negative a billion or a negative a trillion or something like that. Okay, the same thing would work. Okay, so that is not a good question. How about we have 3 positive numbers whose sum is 100 and whose product is as big as possible? This is our new quest. So find 3 numbers, let's call them x, y, z, whose sum is 100 and whose product is as large as possible. Okay, there's the quest. So written in Lagrange multiplier language, we want to maximize some function f of x, y, z subject to some constraint g of x, y, z, which is some function of x, y, and z, equals some constant. Okay, let's do it. So we want to maximize what? X, y, z, their product. Awesome. subject to the constraint. X plus y plus z equals 100. Nice. Okay. Aha. And x, y, and z are positive. Nice. Agree. Okay, great. So this is like not a constraint curve. It's just something we're taking into consideration. Okay, so let's write out the Lagrange multipliers equation. Maybe I'll write that out. Lagrange multipliers equation. It says gradient of f is lambda times gradient of g. So gradient of f, let's see, yz, xz, xy is lambda times gradient of g. 1, 1, 1. 1, 1, 1. Okay, so this gives us three equations, one in each coordinate. It tells us that yz equals lambda, that xz equals lambda, and that xy equals lambda. And then finally we have our constraint, x plus y plus z equals 100. So here we have our four equations and four variables, and we can solve. So let's first see what's going on here. I'm going to draw it down a dimension. So if we draw it down a dimension, we would wish to maximize x times y. So we'll get the same level curves as before for x times y. But now actually we're only interested in it where x and y are positive. So this is level curves of f of x, y equals x times y, which I'm drawing a dimension down because I can draw it. And then our constraint curve is kind of like x plus y equals 100. So those are like this. So this is curves of the form x plus y equals a constant. So you can see where the points of tangency are going to be. They're right along here. So we expect to get something like that. So let's try it. So let's say, equations 1 and 2. So we have yz equals lambda, that's equation 1, and also xz equals lambda, so this is equal to xz using equation 2. So we have yz equals xz. I'd love to be able to divide by z. Boop, boop. Can we do it? Yeah, why can we do it? Because they're all positive. Okay, so it's okay to divide by z because we know z is positive. So we get y equals x. And then using, let's say, equations 2 and 3. So in equation 2, xz equals lambda. That's equation 2. And equation 3, lambda equals xy. So we have xz equals xy. Again, we can divide by x because it's positive. So we get z equals y. So together, these tell us that x equals y equals z. And that's exactly what our picture showed us. Up in three-dimensional space, these blue things would be surfaces, like a family of surfaces, sort of like an onion. And then these red things would be planes cutting through. And so these are tangent to each other, just where x equals y equals z. So these are all the ones. And then we care about the specific one, where x plus y plus z equals 100. Like this is the one that we like. So we now plug into constraint. We have x plus y plus z equals 100. So this tells you 3x is 100. So x is 100 over 3, and so is y, and so is z. Okay. Which is what you suggested at the very beginning, taking them all equal. Okay. So there's a couple of things you might worry about. You might worry that actually we found a min rather than a max. So to check, let's check. We could compute f at 100 over 3, 100 over 3, 100 over 3, and we get whatever value it is. And then at a nearby point, we could check f at like 33, 33, 34, which is nearby. And we'd want to make sure that this one is smaller than the one that we got so that ours is a max. And I think it is, right? I have computed some numbers. This first one, the f at our point, comes out to something. 37,037. And if you do a nearby point, you just get 37,026, which is less. So, good, it's a max. So, indeed, f is a max. And then you might want to know, well, what's the minimum of this function? Lagrange multipliers didn't pick it out. But notice the minimums would occur like along the axes. Like we said, our numbers had to be bigger than 0. They'd occur here, and the curves aren't tangent to each other there. So the Lagrange multipliers method just isn't going to pick out those points. You'd have to find them some other way. It only picks out like local maxes and mins along the boundary. Yeah. Yeah. Questions or ideas? Yeah.
In order to check for a max, we also kind of go to the opposite end of our bounds. So right now we have x, y, and z being as close together as possible. We also say, well, what happens if x, y, and z are as far apart as possible and 2 are 50 and 0. And if that's value is smaller, we then say we were at a max.
Yeah. So it pulled out that in order to find the point that it pulled out had x and y and z as close together as possible, and then you might want to try them far apart and see if that would give you a min. So see if it gives you something bigger or something smaller. Yeah, that's a good idea. So if there's far apart as possible, one would be like 100, close to 100, and the other two would be like close to 0, something like that. Yeah. And you'll see that the number you get is close to 0. Yeah, nice. All right. Yeah, other questions? Isn't it so beautiful? Yes. Good to be alive. Okay. Okay, so here's something that happens. Sometimes you have a thing and you want to send it to your friend through the mail. This happened to me yesterday. I sent my friend a small wooden donkey through the mail. I know, right? It's great. But it was very small. But if you want to send something big, there are restrictions on this. So if you go down to the post office, which is near the traffic circle, you'll find that if you bring like an elephant, for example, they will not allow you to mail it. There's usually some restriction. So maybe it's a restriction of the form length plus width plus height of your box has to be less than, I don't know, like 100 inches, something like that. So let's find, suppose that was our constraint. Our elephant will have to be pretty small. Suppose that our constraint is that length plus width plus height of our box has to be less than 100, and we want to send the most, I don't know, peanuts or something to our friend. Can you find the maximum possible volume of such a box? Yeah. Shall we do it? We already have, right? Yeah, so this is a, other way of thinking of the same thing. If length plus width plus height have to equal up to 100 and you want to have the largest possible volume, it's just x plus y plus z is 100 and you want to find the biggest possible product of those numbers. So we already did that. So let's do something else. So suppose you want to find the maximum volume of an open-topped box. These come up a lot in calculus. Maybe not so much in the rest of life, but they do come up a lot in calculus. So here's our open-topped box. It's closed on the bottom. And let's say its height is z, and its width is x, and its length is y. So find the maximum volume of an open-top rectangular box. Well, that's kind of unconstrained. Now it can be as big as we want. So let's say we have a fixed amount of cardboard. So made of 12 cubic centimeters of cardboard. Okay, there's the dream. Good. So maybe instead of sending your pine nets to your friend, you just simply want to carry them over to your friend, and all you have is 12 cubic centimeters of cardboard to make it happen. So sad. Let's do it. So we want to maximize some function, f of x, y, z is something, subject to the constraint g of x, y, z is something of function of variables equal to some constant. Okay. Is someone willing to do it? Yeah. Awesome. I will give you a better piece of white chalk. And can you speak loudly, please?
We're just trying to maximize this volume, so it's x, y, z, and then we're just trying to add all the, I guess, the areas of the different surfaces. So it's 2 times y.
Can you hear Ife? You have to speak up louder.
Okay, so we want to maximize volume, so it's x, y, z, and then here we just want to add up the areas of the, I guess, the surfaces. So there's 2 times y, z, because you have the 2 sides here, plus 1 times x, y, which is the bottom one, and then plus 2 times x, z. And this has to be less than 12 centimeters squared.
Nice. Yeah, and since we need to maximize it, we'll let it be. We'll make it be equal to 12 centimeters squared, because it could be less, but we know it'll be better if it's more. Nice. Would you be willing to write out the Lagrange multipliers equation too? I'll give you some space. You will love it. Or you can pick a friend to do it for you. Okay.
You know, the gradient of this one is just, you would take the partial derivatives, so yz and then xz xy equals to lambda times, this is it's actually, it's plus 2z.
Nice. Great. Yay. Great job. Yeah. Okay. So we have this Lagrange multipliers equation, which will give you 3 equations. The first coordinate, the second coordinate, and the third coordinate, plus the constraint equation would give you your 4th equation. 4 equations, 4 variables you could solve. Okay. So that's the idea. We'll play with this more on Monday. And thanks for coming. All right.